We call our moon camp Elcano, honoring the Spanish navigator who completed the first circumnavigation of the Earth. At the lunar south pole, there are impact craters which permanently dark bottoms. We chose Shackleton crater because its edges are exposed to light almost permanently, and its interior will provide us with frozen water and protection. Near the base, we will build the landing platform.
The camp will accommodate 4 astronauts. It will be made up of semi-spherical modules connected and with 2 outputs. The central module will consist of the kitchen, dining room, gym, and common room. There will be another module which consists of a rover's garage, another module consisting of a workshop and a control room, the greenhouse, a laboratory and nursery, some bedrooms and toilets, and all the modules will be connected by corridors.
We will also take care of their psychological well-being by projecting images of the Earth's sky through artificial intelligence, changing the intensity and color of lights, emitting relaxing sound, and also providing a robotic pet. Though Moon proximity allows video conferences with loved ones in Earth.
The modules will be constructed by rovers transported from the gate along with deployable domes. On top of these domes, using 3D printers, the rovers will begin building an infrastructure in a networked pattern with regolith, following the cellular printing method proposed by the company Foster and Partners, in collaboration with the ESA. And this is a lightweight but sturdy structure that will be filled with more lunar regolith over time.
In their daily routines, astronauts will dedicate 3 hours to exercise and 8 to base maintenance and research.
Robots with pressurized tanks will collect ice from the crater to liquefy it. We will also extract water from lunar regolith through filtration or distillation. Additionally, we will collect and purify water from urine and respiration through osmosis.
Although initially we will rely on packaged diet, we will eventually become self-sufficient and achieve the 2800 kilocalorie needed for each astronaut thanks to a greenhouse. LED lighting systems with specific wavelength lights will stimulate plant growth. We will opt for vertical aeroponic crops, which consume very little water as it is sprayed onto the roots, make the most of space and minimize the risk of pests. We will cultivate soybeans, potatoes, carrots, turnips, dwarf wheat, strawberries, and tomatoes. Using 8 rotating towers of aeroponics, we will produce 960 plants at different stages of growth, harvestable between 10 and 30 days. We will produce electricity through photovoltaic panels built with iron pellets from the regolith, installed on the crater's edge. A 0.4 hectares will generate about 100 kilovolts. We will maximize their performance with heliostats. We will also produce electricity through radioisotope batteries and fuel cells, which directly convert hydrogen and oxygen into electricity, water, and heat.
The location and construction with regolith will protect astronauts from meteorites, extreme temperatures, and solar radiation. Hermetic hallways will prevent depressurization in case of a problem in any module.
In habitable domes, we will create a breathable atmosphere. Plants and algae in the greenhouse will produce oxygen, using CO2 from respiration and water from urine for photosynthesis. The iron and titanium from lunar soil can catalyze water electrolysis extracted from the regolith itself, producing oxygen, hydrogen, and methane from solar radiation and exhaled CO2. astronaut feces will be anaerobically decomposed by microorganisms. Methane obtained will allow us to cultivate methylococcus in reactors and produce biomass rich in proteins and fats, which is edible from astronauts or for insects that we may raise in the future. Further research is needed for menstrual waste. Regarding spacesuits, we will need to collect waste and investigate solutions that facilitate multi-day expeditions away from the base.